Okay, there we go, perfect. So that's not the title that was up a moment ago, for which I apologize. The original title was kind of grandiose, and when I was trying to put the talk together in the abstract as well, I realized there was far too much to squeeze into 40 minutes. I think I originally proposed to talk about like 5 big threats to valid inference, and I'm going to talk about one. So I apologize. But I do think it's actually a good opportunity for HBM to bring me back the next 4 years, so I can tell you, each year I'll talk about one of these things. That's my strategy. So I'll talk about generalizability, which I think is a really important and underappreciated issue that pretty much all of us have to contend with. Probably will not be objectionable if I suggest that generalization matters, right? So if we talk about this as purely induction, so the idea being that we reason from the specific to the general, right? So we observe individual experiments, but we want to make claims that are broader than just the particular context we operate in. Nobody, I think, will take issue with that in much of science, at least, induction is absolutely critical. And most findings in neuroimaging, I would argue, are only really interesting because we expect them to generalize broadly. So it would not be interesting for most people here if I presented some new finding and said, but wait, this only applies in Austin on days when the temperature is above 95 degrees, right? And I'm the experimenter. Probably wouldn't care very much. So that's the fundamental claim, which again I think is not controversial, but I think it has some interesting implications that we haven't, as a field, necessarily worked out and applied. And so that's going to be what I'll try to unpack today. But because I want people to remember the talk positively, I thought I would start with cute pandas. And then whatever else happens, you'll probably come away thinking, that was not a terrible talk. In fact, have some more pandas. These ones are happy, right? You go on the internet and you Google panda, you'll find lots of images of pandas being cute and happy, but sometimes they're also sad, right? So there are sad pandas too. Here are some sad pandas. And sometimes pandas are just hanging out. They have no expression at all. They're neutral pandas. So of course, just to kind of set this up, right? Imagine you're trying to kind of contort yourself into some hypothesis you can work with here, just to illustrate the point. Well, you might say, look, it's an interesting question to know whether human beings use the same neural mechanisms to process facial expressions in the pandas and humans, right? Lots of work on how we process emotion in humans. Might be interesting to try and see whether that applies in other mammalian species as well. And so you might do the very common thing in task-based fMRI. This is the famous logic of subtraction, right? So if you start with a happy panda or a sad panda, let's say, and you subtract a happy panda, whatever remains must be the difference between those two things. And so if we pretend that's a very clean manipulation, and you use pictures like the ones I just showed you, maybe you have 20 happy pandas, 20 sad pandas, the difference is presumably attributable to that emotion condition, right? And again, since we're making this up as we go along, we can pretend we get this beautiful map. This is actually the emotion map from Neurosynth, so you have to believe that this is what the brain looks like on emotion, right? It's based on like 800 studies. Let's say we get this beautiful picture. Again, this is all by hypothesis, so we don't have to worry about the methods. The question I want to take up, though, is what should we conclude from this, right? So let's say we get these results and we have an actual study there. And I would argue this is very typical. There are thousands, literally, of task-based studies that follow this basic sort of idea, right? So you set up a contrast between two conditions, you get some result, and you want to conclude something. So the critical thing to keep in mind here is that, of course, as I already mentioned, we are operating in a particular context in this study. So we studied a small number of subjects who were responding to a small number of panda images at one research site with just one experimenter, right, typically. But of course, that's not particularly interesting. We want to make some broader claim. We want to talk about pandas in general, maybe mammals in general, emotions in general. And the question is, what universal observations are we entitled to generalize our conclusions to? So this borrows the idea of a universe of admissible observations from generalizability theory. And the idea is implicitly, maybe not explicitly, but implicitly when you make a claim, there is some set of observations that you would say, yes, it applies there, it does not apply there. Right? So the question is, what's inside that universe? And so we're asking the question, how do we decide, in some sense, on what that universe is? Can we just choose? Can we just say, look, this is what I think this generalizes to, or not? And we can consider two different ways of doing this. This is really mostly just rhetorical, so setting up a fast strategy and a slow strategy. And I would argue this is true almost everywhere in science. You have this choice between sort of fast generalization and slow. So when we're talking about fast generalization, the idea here is we can afford to dream big, right? So we can say something very sort of broad and far-reaching like this. Imagine this could be our paper title. Increased amygdala activation in response to affective mammalian expressions relative to neutral mammalian expressions, right? That's very broad. And you might look at this and say, That's not really dreaming big at all. This is a very typical title for an fMRI paper. Yes, and that's exactly the problem, right? But this at least seems clearly we're extrapolating beyond what we actually know from this one study we did. And it seems pretty interesting, I would argue. Not everyone in this room will agree, but I would probably skim a paper with this title at least. But again, you have to kind of worry about all the inductive leaps we just took. We had one set of stimuli. We didn't say anything about that. We had one set of subjects. We're making a fairly broad claim. We could have gone the opposite route. We could have used what I would call a slow generalization approach, which is very careful and cautious. And this might be the title that we use then. Maybe it's greater amygdala activation in 22 UT Austin undergraduates when viewing images angsty tree panda.jpg and panda-delight.jpg, then image panda goes meh.jpg, right? This is perfectly reasonable. I mean, it's actually much closer to the actual finding. But it has this unfortunate property, which is that it's kind of boring and probably nobody would read this. In fact, you would probably wonder what the hell this is doing in a journal. So if I were to ask you a show of hands, I won't, but if I did, which of these titles you prefer, I'm pretty sure everybody in this room would say I prefer the FAST, right? That's an interesting paper, and it says something potentially scientifically interesting. However, I would argue this is not actually a matter of preference, right? So I kind of, we can present it as such, and it might seem like it's really up to you. So you typically prefer, all of us typically prefer, for our conclusions to hold in general. So in the case of the panda images, we would like to believe that any difference we see in brain activity holds not just for those particular pictures we sampled, not just for those particular subjects, but more generally, right? For other stimuli and other subjects like the ones that we studied. Unfortunately, our intentions have very little to do with this, right? So what we do get to choose is what we want to generalize to. But once we've done that, once we've decided, once we've said, look, I expect, I want this inference to apply broadly to this population, then the statistical model is constrained. It has to respect that desired inference, right? We can't just fit a model and then draw whatever inference you want based on that, right? So you have a parameter estimate, you say, oh, good, this must apply everywhere, right? In fact, the model has to account, and I guess we're talking about stimuli, it has to account for the variance that's introduced by the stimulus sampling process. There's actually a process there that we have to account for because we don't care specifically about these particular stimuli. And that's really the point of departure for the rest of this talk. And because I always forget, I will thank the other people involved in this, Jake Westphal, my former postdoc, and Tom Nichols, who probably needs no introduction. This is really going to be just about one paper, and I realize it's a little bit weird to talk about one paper and not an entire program of research, but I don't really have a program of research, so I'll talk about this paper. I think it's important. It feels as important to me as other stuff that I've done recently. And so to kind of give you a sense of where we're going with this, we can start by talking about the distinction between random and fixed effects. So how many people have heard these terms used? Right? Okay, how many people feel confident they know what the distinction between random and fixed effects is? Okay, so many people have heard these terms. Large number, but fewer people feel they can give a confident description of what these means. There are lots of definitions in the literature. They are related in various ways. For present purposes, I'll use the following definition, although most of the others will also work okay. We are going to say that effects are fixed if the observed levels are of intrinsic interest, and they're random if they're only interesting as exemplars of some underlying population. Okay, again, there's variations on this theme, but that's one way to think of this. So for example, subjects are almost always treated as random factor in our studies. And that's because we don't generally care about these particular subjects, right? So Amy and Ramesh come into your study, great, they're maybe very nice people, but you don't care about them in particular. You're trying to make claims about people like them, some population. Whereas if you think of maybe like an n-back task and you're manipulating load, 3-back versus 2-back, that's considered fixed because it's not like you're sampling the load from some distribution with a mean and variance, right? It's not like it could have been 7-back that walked through the door. I mean, these are the particular levels that you care about. So that's one way to think about this distinction. And these are modeled very differently. And so you might ask, well, why do we even care? Like, why do we care about this idea of like random effects? And just to give you a simple intuition, I can give you an example that probably everyone in this room is familiar with. So suppose we have 100 trials for each of 20 subjects, 50 per experimental condition. So this would be the very classic sort of one sample t-test, right? You have a bunch of subjects, each subject had a bunch of trials in one of two conditions, and you're going to do a t-test. Now, as most of you will hopefully agree, the appropriate one sample t-test here is conducted at the level of subjects, not trials, right? You wouldn't take 1,000 trials here, 1,000 trials here, and compute the t-statistic. You would do this typically by first averaging within subject and then do the test on that. Or you could fit a hierarchical model, which would be essentially equivalent, right? But the idea is that you're doing this at the level of subject and not treating every trial like it's an independent observation. And the reason we do this is because we intend to generalize to new subjects. And there is a certain covariance structure of these observations, so the trials are correlated within subjects. And so it's not like the trial comes from you is the same as the trial that comes from me. We have to model the fact that there's this between subject variance. And this, I think, is completely uncontroversial. Again, we all model our data this way. If we ignore this between subject variance, then what we're going to do is we're going to make it look like that fixed effect of interest, the condition difference, is actually much more precisely estimated than it is, because a lot of that variation actually comes from the subject variance that we would otherwise ignore. Right. So again, this, I think, is not controversial. But the question that I think is more controversial is why would we stop at subjects, right? Like, why would we model subjects as random and not much else? And in fMRI, we always model subjects as random effects, at least now. That was not always the case. We never model stimuli as random effects. So as far as I know, I think this is still accurate, there's never been a study that has modeled stimuli as random effects in context of fMRI scanner. There are two studies that I think were ahead of their time that came very, very close, and they talked about similar kinds of issues, but they didn't actually apply this and sort of examine the consequences. But the key point is that the logic really should be, I think, exactly the same for stimuli as for subjects. And this is a point that was made first in the psycholinguistic literature now over 50 years ago. So if you're looking at this thinking like, wow, really a talk that's basically about a statistical point made more than 50 years ago in a totally different domain, you're not wrong. I mean, that's really what this talk is. But I think the consequences are important, and we haven't thought about them enough, and I think we should. But the claim is that there's nothing there's no reason why we should treat subjects as if we care not about these particular subjects, but about the population they come from, but change things up for stimuli so that we act as if we only care about the exact same stimuli we used, right? I don't think that's the case. And if you think about how what this looks like in a typical fMRI model, so here's a model that will, I think, look very familiar to many people. We'll pretend it's an related design. There's no jittering, but the idea is basically that, right, so if you have this, let's say, two conditions, I think they're nouns and verbs, and you have this red condition and the blue one, and the data might, when you fit this model, the data might show you that, in fact, it looks like there's a larger parameter estimate for the red condition than the blue, so for nouns than verbs. But notice that almost always we ignore the fact that there are different stimuli here. There's chair, tree, spoon, etc. We would assign these all to the same regressor, right? And so those cannot vary independently. Now, that is on its face a crazy assumption. Like, if someone asks you, do you really think that these individual stimuli all produce exactly the same brain response, I think it's hard to believe that the answer could be yes, right? It might be small, but it's not going to be zero. And yet this is the model we fit almost everywhere, actually everywhere, I think. So we could think about what we call a random stimulus model, where we allow these individual stimuli to get their own effect, essentially. And now they can vary independently, and so they can take on different levels estimated from the data. And so that's really the essence of this model, is we're doing for stimuli what you would already do for subjects. And so we can simulate to get a sense of what this would look like. And in particular, what would happen if we don't include random stimulus effects, right? So this is if we apply the standard model in a situation where there is stimulus variance, which is always really. So for the purpose of this first simulation, we'll just assume that there's no true difference between sad and neutral pandas, or any conditions you want. There's no labels here. We assume that there's roughly equal subject stimulus variance, and that's actually a reasonable assumption, given the data we looked at. And let's sample 100 subjects, and we have 16 stimuli, 8 per condition. Right? So here's the traditional model. It's a simplified version of what you would fit in fMRI. We're leaving out all the fMRI-specific stuff. But the basic idea is that you have some fixed effects of interest. We care in particular about this beta here, which is the condition effect. But we recognize that there's between subject variance we need to account for. We have both random slopes and intercepts. And we can model this in a Bayesian framework, but it doesn't have to be. And the idea is that there's some normal hyperprior on those random effects, and plus some error. And if we fit this, remember, if this model is properly calibrated, given the setup I just gave you, then it should show nothing, right? I mean, the parameter estimate should be centered on 0. First time out, we run the simulation, and it's not centered on 0. In fact, you can see that there clearly is, the model thinks there is some large effect there, right? This is not cherry picking. This is the first time out. You think, maybe I got really, really lucky. OK, we tried again, and now we get, again, a non-zero parameter estimate, but it's in the opposite direction, right? Even though by hypothesis the effect is 0. So there's something very strange going on here. And if we repeat this, then much of the time, certainly more than 5%, you will see the probability mass depart significantly from, well, I shouldn't say significantly, but meaningfully from 0. So all we have to do here is change the model slightly, and we add a random stimulus term. Right? So now we allow every stimulus to have its own intercept. And again, it's constrained by a normal hyperprior. So this is actually, we can actually estimate this. It would be non-identifiable in a classic with least squares estimation. And we can rerun the simulation. And so now, first time out, this looks OK, right? I mean, still a lot of the mass is on 0, so you wouldn't probably conclude anything from this. And you can ignore that. And if we do this over and over, sure enough, it looks like the model is now getting it right. And it should, because this is the model that matches the way the data were generated. But the standard model is not. And so, of course, this is just like one toy example. But we can, of course, do this hundreds and hundreds of times and then summarize the results. And here's what we see. So if you look at these rows, this is the amount of stimulus variance. So if you look first at the case where there is no stimulus variance at all, which is what is assumed by the standard model, right, because it's equivalent to saying the stimulus variance is 0, then if you focus on the type 1 error rate, for example, when alpha is 0.05, let's say you have 32 subjects and 16 stimuli, seems like a pretty reasonable setup. Then you can see, well, actually, sorry, the point here is that we control type 1 error at the nominal rate, right? So this is the standard model, and when there's no stimulus variance, you're fine. This model is fine. But the interesting question now is what happens when you actually when the stimuli do have some variance, when they have some effect on brain activity. And so in a case where there's a lot of stimulus variance, for example, but not an unreasonable amount, I think, now if you have, let's say, 32 subjects and 16 stimuli, false positive rate is close to 50%, right? And it's not going to be systematic in terms of direction. So sometimes it will go one way, sometimes it will go the other. But the point is you will get excited much more often than you should. And this is still true if you have an alpha of 0.01. In fact, proportionally, if you look, for example, at 32 subjects, 16 stimuli over here, 20% false positive rate. So that's a 200 times inflation of the nominal rate, right? So that's not good. And if this seems like hard to believe, remember, the false positive has specific meaning here. It's not that this is driven by noise. There's nothing going on. It's that you are concluding that this is an effect attributable to the condition, and it's not. It's attributable to the stimuli. So there can be a perfectly real difference between the stimuli you've sampled, but it does not reflect the condition effect which you care about. You just happen to have some stimuli that are high here and low here, and so on. And just to show you this is not at all specific to fMRI, my postdoc Jake has done this before in a very different domain. So this is in social psychology using parameters that are realistic given social psychology studies, and you get very similar results. So you can easily get upwards of 50% false positive rates without, And one point I'll point out is that this problem actually gets worse as sample size, or as subject sample size increases, right? So typically we tend to think like, well, throw more subjects at it, things get better, power increases. But actually, if you don't have the right model, what will actually happen is as your subject sample size increases, your false positive rate, if there's large stimulus variance, will basically go to 1. So if you have 10,000 subjects, you're pretty much guaranteed to find something, right? And you can think of this in some ways as sort of the argument about the null always being false, right? The null is always false. The question is why it's false. And one reason is because you happen to have picked stimuli that are driving the effect, that are not perfectly identical. This is still simulation data, right? So now we can turn to real data, real imaging data. So here's data from the Human Connectome project. And I'm going to use mostly HCP data, but I do want to make clear, this is just for convenience. I mean, I like the fact that the HCP data is available. There are large samples. There's preprocessed data. So it makes it easy. But I don't think anything I'm going to show you is atypical. Right? This is not selected because there's anything unusual about the HCP data. It's just convenient. And I will show you some other data sets, too, that were also convenient to grab. And so what you're looking at here is the amygdala response to the emotion task in the HCP data. And there's sort of 3 columns, and that's because there's 3 types of stimuli in this task. There's shapes, really just essentially ellipses. There's angry faces, and there's fearful faces. And this is what you see if you estimate each subject's response to each of those 3 stimuli. And rows here are subjects. So you look at this and say, well, clearly there's some variance across subjects. But overall, the dominant pattern is that the amygdala is much more responsive to faces than shapes. And it looks like it's actually also more sensitive to angry faces than fearful faces, right? And those both seem like fairly robust patterns. But here's what happens when we add those stimulus effects. Right? All we're doing is we're adding an extra set of parameters for the stimuli. And look at how much variability there is within those 2 conditions. Right? So there's really no difference for the shapes. But within each of these face conditions, there's tremendous variance. And arguably, that variance dominates the difference between these 2 categories. And so it could just be that we happen to have sampled unusual faces into anger or face conditions, right? And in fact, that is actually what's going on. One nice thing about this I won't talk about, but it is nice that you can actually go and you can actually use these parameter estimates for individual stimuli now to ask interesting questions, right? So these are the posterior probability distributions for each of these individual stimuli in the HCP data. And so you can now pull these out and potentially go and relate them to other things. You could build regression models or whatever that are now using stimulus level estimates, which you couldn't otherwise. And so you have another source of variance that you can use in further exploration and hypothesis testing. But I won't talk about that anymore. What I do want to show you is what happens if you think of this purely in terms of a test statistic or something like a test statistic. So here's what you would normally report. This is the standard model. This is, again, the amygdala. This is real data. This is the amygdala response to shapes, faces, and angry faces. Shapes, fearful faces, and angry faces. And as I just mentioned, you look at this and say, wow, look at that huge effect of faces versus shapes. And also, the anger and fearful face distributions are almost disjoint, right? So that seems like a pretty interesting thing, too. But here are the same curves with the random stimulus model. You still would probably conclude there's something, there's some differentiation there for shapes versus faces, but there's really nothing meaningful going on as far as the faces go. So you've gone from something that you could potentially tell a story about in the top panel, and you could write a paper saying, wow, it looks like the amygdala cares more about angry faces. Why is this? We need to explore this, right? But actually, probably the simple explanation is you just because of the randomness of the world, essentially, you've sampled stimuli that are not perfectly identical, and there's no meaningful thing there to explain at all as far as the anger versus fearful faces goes. It's just a quirk of your sampling. If you fit the right model, then you don't end up chasing that down the garden path, right? You just observe that and say, okay, fine, never mind. Here's what this looks like when you look at it at the level of the whole brain. These models are very hard to estimate. They're computationally intensive, and so we can't do this at a voxel level. So we did an ROI level. But the point, I think, should be clear, and I don't doubt it'll hold either way. So what you're seeing in the top panel over here, every point is an ROI. There are 100 regions. And the x-axis is, I believe, I guess this is not clear. I can barely make it out. But I think this is the standard test statistic. No, I'm sorry. The standard test statistic is, or the z-score is on the y-axis, and the it's a correct, or more correct at least, estimate is on the x-axis. And so if these models gave you the right answer, then they should basically lie along the diagonal, right, the identity line. But they don't. You can see that the standard effects are getting squashed dramatically. So that, for example, in one case, there's one region that has a z-score of like 30 in the canonical model, but actually is very close to 0 in the random stimulus model. And you can see that you would end up drawing very different conclusions. This is what you might report with the standard model, but you probably should actually be reporting this. There is literally nothing there, given this data set, at least. There's no difference between anger and fearful faces, right? And even for shapes versus faces, down here, the only ROI that shows an effect here, in this case, is the amygdala. There's actually an interesting reason why, even though you would think of like maybe the FFA should be sensitive to this, but the FFA actually shows huge variance as a function of different stimuli. Right? It shows a different response for some stimuli than others, and there's so much variance that it's actually not as robust at distinguishing between shapes and faces. And so paradoxically, a region that's actually representing faces, maybe not on, it's not the central tendency, but the variance is actually not necessarily going to show you the most robust effect in this comparison. But the takeaway point is, you get a very different answer, and in some ways it's a less compelling answer, but it's probably closer to what's actually going on. And just to show you this is not cherry picking, the top two panels are what I just showed you, the top two rows, but now we're adding 3 other data sets. So here we have, I think this is HCP working memory task, 2 back versus 0 back, similar kind of story, social cognition task. I should add, so in the original talk I was going to give, I was going to try to avoid using these labels because I would argue these tasks are not really working memory tasks, they're not really social cognition tasks, but that's it. They are labeled as such, so we'll stick with that. But the point you can see is clearly you get a dramatic compression of the z-scores. Here's a case where that doesn't seem to be as dramatic. This is a data set from a study by Luke Chang and colleagues, a data set from Peter Generis at Pittsburgh with IAPS pictures. And so for whatever reason, you still get a reduction, but it's not as dramatic, and it could be the number of stimuli is larger. I don't remember off the top of my head. Okay, so what's the bad news? Well, you just saw it, right? This problem is pervasive in the fMRI literature. Again, I could be wrong, but I'm not aware of any study ever that's actually modeled stimulus as a random effect. We estimated in our paper that this affects at least 50% of published tasked fMRI studies. That's not an estimate we pulled out of a hat. We, and by we I mean, of course, my postdoc Jake, coded 100 randomly selected studies from Neurosynth, conservatively, so this is actually probably a lower bound, and I think the estimate is something like 58 out of the 100 look like they should use this kind of model, given the nature of the design, right? So I think that's a conservative estimate. The magnitude of the problem is often going to be severe, and you've already shown you that. I've shown you all the data sets we analyzed, with maybe one exception, which is similar. So this is not cherry picking. In most of the test data sets, we see effect sizes drop by 50 to 90%. I don't know how representative that is, but I have no reason to believe it's not going to be representative. The number of stimuli used in these studies is very similar to what's out there in much of the literature. And so I think it's inevitable, the inevitable conclusion is under realistic assumptions, the false positive rate in the literature is likely to be high. Now again, I want to be clear, right, because false positive can mean different things. It's not a high false positive rate if you constrain your interpretation to these particular stimuli. Then, ignoring all other kinds of issues with fMRI data, if everything was done by the book and so on, then fine, you can say the nominal rate holds for these particular stimuli, right? But if you were trying to generalize and say that your finding applies more broadly to pandas, to affective faces, to words, et cetera, then it's very likely the false positive rate is really quite high. How high, I really don't know. We can say that over half of studies have probably inflated effects. It's an open question as to how severe the problem is, but I suspect, it's probably going to be closer to 30 or 40% than to 5%, if I had to guess. Problematically, there's currently no support for fitting these kind of models in any of the major analysis packages. So you can't do it in FSL, SBM, or AFNI, as far as I'm aware. I could be wrong, but I'm pretty sure that none of those out of the box. You could, of course, write your own code, which is what we did, but of course, that's not scalable necessarily, and it doesn't help everyone else in this room. And so hopefully, if there are people working on these packages, someone will do the really hard work. I mean, it's easy to stand up here and talk, but someone will actually do the hard work of implementing the ability to fit these models in a scalable way. Okay, so that's the bad news. But there is actually some really good news, I think. And the good news is this behavior is really quite predictable. So just as with subjects, right, why do you sample more and more subjects? Because you want your estimates to be more and more representative of the population, right? I mean, the more subjects you have, the more precise your estimate gets. And the same logic holds here. When the stimulus sample is large, then the RSM and the standard models converge. And at the limit, if, for example, every subject gets a completely different set of stimuli, these models are identical. It doesn't make any sense to fit the RSM. And so the moral of the story here is, until we have the ability to fit these models, use large stimulus samples whenever you can, because that will actually largely circumvent the problem. And you can present different stimuli to different subjects. So perversely, there's sometimes this argument that we should give everyone the same treatment because we want to maximize power, but you're only maximizing power if if you care about those particular stimuli, right? If you care to generalize, you should do the exact opposite. You should give every subject a completely different set of stimuli, and that is how you maximize power to detect at least the main effects, if you don't care about the interactions, and that's a different story. So it's helpful to present different stimuli to different subjects. And just to show you that this actually works in practice, here are two other data sets we analyzed. The top one comes from OpenFMRI. This is a small data set. I think we only used 11 subjects because that's what the subjects that had all the data we needed. This is from, I think, a study done by Jessica Cohen in Russ Poldrak's lab. And the key takeaway point here is that there's really no difference in the estimates you get from the standard model and the random stimulus model. And the reason is because, it has to be because there are 120 stimuli, and different subjects get different subsets of those stimuli, right? And so it's very easy then for the model to figure out essentially what's an effect of this particular stimulus versus what's an effect of the condition, because there's enough stimuli there that you can actually separate those things cleanly. The bottom one is more interesting. That's the HCP language task, which is contrasted with the math condition. And what's really interesting about this to me is that the language condition, which is a set of stories, has, I think, something like 8, maybe 10 stimuli that all the participants get. But the math test is adaptive, and every subject gets a different, or almost every item is actually unique, and no other subject in the data set actually gets presented that math problem. And so you would predict, if this account is correct, that the posterior estimate for the math condition should not change much, and sure enough, that's what you see, right? Very little change between this and this. But the uncertainty for the story condition expands dramatically, right? And so that's a nice demonstration of this principle, that if you just sample more stimuli, then you can largely avoid this. And I'm not saying you shouldn't model this statistically, but if you don't have the ability to, then at least, if you can, try and use large stimulus samples. And the really nice thing about this, it's not always feasible, but unlike subjects, right, typically you don't have to spend more money or not much more money to sample new stimuli. So you spend more time maybe to find something like 100 images instead of 20, but you don't have to pay any more. You're just given different subjects, different images. There's no increased scanning costs, right? And so if anything, this is arguably a much easier problem to deal with than low power in the subject-wise sense. Okay, I'm actually running ahead of schedule, but I'll slow down and start speaking. I know I speak fast, so this should have been good to realize like 20 minutes ago, but nobody yelled at me. The people in the front are supposed to tell me if I'm speaking too quickly. Okay, so I'll just make a couple of other points about this. And I can take a break and drink some water. Good, that's better. So I've talked so far about subjects peripherally, but mostly about stimuli. Some of you might be looking at this and thinking, that's great, but there are other things that we care to generalize over, right? So it's not just subjects and stimuli. The same logic presumably applies to other random factors. So you can think of things like scanner, right? Research site. Research site you can probably think of as a random factor. I mean, the study could have been done in other places, different cities, et cetera. Experimenters, right? Anybody in this room presumably could, to a first approximation, do any study that someone else handed them in this room. Possibly even things like font face, right? So I find it plausible that somewhere out there, right, somehow, somewhere, there is a study that published some results, and those results are invalidated because the authors presented the stimuli in Comic Sans, right? That is not, I mean, it's not crazy to think that somewhere, somehow, that has happened. And so all these things and many, many others are things that we might want to actually think about, because implicitly we already are generalizing over them. We don't think that these results only hold for the fonts we used, right? But the real problem with this is that unlike subjects and stimuli, most of the things do not vary in a given experiment. We generally don't do the same experiment with 3 experimenters in 4 different cities, right? And that's a problem, because if you don't vary these things, then it's very hard to actually model them, right? There are things you can do, and we're working on some of them to try and sort of get sort of quasi-estimates of what it would be like if you could do this, but it's not, it's not feasible to add to your model terms that don't, as far as you know, exist. There's no variance in them. The point here, though, is that the actual false positive rate, if you think about the claims we make, so I've showed you that just one factor, although it's a big one, can inflate false positive rates to a ridiculous rate under reasonable assumptions. But of course, once you start thinking about all these other things that we implicitly, clearly are generalizing over, but are not modeling, the actual false positive rate must be even higher. And so one way to think about this, again, is it's not necessarily that it's a false positive. It's that there could be context-specific factors. So maybe the effect works at UT Austin and it doesn't work somewhere else, but it's not because, it's not necessarily that I cooked the data or that there's experimental bias. It could be that there's a systematic factor that distinguishes places where it works from places where it doesn't, and that's okay, but that's not the claim that I make when I write a paper. I don't say, like, here are some things that I think would prevent this effect from obtaining if it were done in Seattle or in Florida or, in Leipzig. If you do say that, if you explicitly specify that you're not interested in generalizing to new levels of the non-varying factors, then there's no problem. And the false positive rate, again, it's weird to think that the false positive rate depends on your intention, but it does, right? If you are not making the claim that this is meant to generalize, which of course makes your claim much less interesting, but then you're okay. You don't have to worry about this problem. You just have to worry about the reader saying, well, I don't care so much then. Let me also point out something else which is interesting, which is that this isn't true just for inference, right? So I've talked so far about sort of estimation and in the context of hypothesis testing and asking whether there's an effect or not. But most of this really goes for prediction or classification approaches too. The difference is that instead of talking about random effects, we can now talk typically about cross-validation schemes, right? So this accomplishes largely the same thing. So the idea is that in the context of stimuli, for example, you can train and test your model on different subsets of stimuli. And this actually people are doing, fortunately. So one moral of the story, and I think we should encourage more prediction approaches, but one moral of the story is that if you're doing prediction, the same concern applies, but it arguably applies in a way that's more tractable, because I think for most of us, it is actually possible to train a model on some of the stimuli and test out a sample on different stimuli. But of course, the same is true for other factors. And so in theory, anything that you want to generalize over, you should now cross-validate as well. So you might think of testing out a sample on subject, stimuli, if you can, on research sites, and so on and so forth. And people have discussed this in literature. So there's a really nice paper from Wani Wu and Torwager. And this kind of articulates really many of the same points from a predictive standpoint. So the idea is they're looking at biomarkers and what it actually takes to come up with a biomarker that is actually predictive in a generalizable way, right? Because it's no good to have a biomarker if it only applies in this one little sample or this population. It ultimately has to be useful in a clinical situation where it's a somewhat different population in a different context. And the point they make nicely, I think, is that lots of people do cross-validation, but fewer people do cross-validation across slightly different samples, right? And they're focusing, I think, on populations. But the same point would apply for stimuli. And once you get to the point of now we're trying to generalize to completely different scenarios, taking a classifier from the lab and applying it to a somewhat different task and different population, then almost nobody does that. And so again, that drop-off is common, I think, with both predictive approaches and with inferential approaches. But there are people doing it for stimuli, at least, and that's nice. And so here's one really nice example. This is from Alex Huth and Jack Gallant. Many of you are familiar with the study, right? And so the idea is to build a predictive model of the neural response to naturalistic spoken text. And so the model is trained on, I think, 7 stories or 5 or something, and then it's tested, right? So we actually evaluate its performance on a different story, a new story. And so that captures the same idea. And you want to be careful about how you do this, of course, and just like you want lots of stimuli, you also want to make sure, ideally, that you're training and testing on many stimuli. But you do have a way of addressing the same underlying question. Another interesting issue that comes up, and I bring this up because this is actually it's a confusing point, but it's important to clarify, right, is what population we're actually generalizing to. And so what modeling a factor as random allows us to do is generalize to a population. This does not mean it's the intended population. Right? So, and in fact, often you won't actually know what the population is. It's idealized in some sense. Right? So I can't actually tell you what the population of happy panda stimuli is. Right? There is some data generating process that could involve like RAs, Googling, and coming up with, and that's what defines the population. But I can't tell you. I can give you sort of like some rough approximation. Like we search for images that have one panda in them, and the panda looks happy, you know. But that's not a very formal definition of the population. And in general, you won't know. You don't know either when the subjects walk in your door, right? You know that they're probably undergrads, but you don't really know what the process was that selected those exact participants. And so the key point here is we do all this, and we have to do all this if we want to generalize to a population, but this should not lead you to believe that you have now solved the problem of representativeness, right? Like it may still be the case that the subjects you've sampled, your effect can be generalized to new subjects from that population, but those subjects can still be weird in the sense of, they can be from a small subset of humanity, and the same thing goes for stimuli, and the same thing goes for research sites, et cetera. And so it's important to keep those two things in mind. Generalizing statistically in this case means to a population, which may or may not be the population you care about. There's still a separate process you have to go through to try and align the population you're sampling from with what you actually care about. But if you put those two things together, so the prediction versus inference and the question of what you're trying to generalize to, then we arrive, I think, at something like this. We can think of these as generalization patterns, like what you would do given the kind of inference or the kind of approach you're using and what you're trying to generalize to. And so we can come up with a table that looks like this. So the idea in the first row is if you don't mean to generalize, and again, this is now we're talking if your intention is not to generalize, not to like just ignore the issue, right? Then you really don't. So I should assume that you have like some factor F you care about, right? So if you don't care to generalize to a population, you really truly care about levels of these particular levels, which might be true, for example, if you're doing psychophysics, right? Like how bright is the light? You're not sampling from some random distribution out in the world. You have a particular parametric design problem, and you do care about these particular levels, so you don't need to worry about this. Right? That's great if you do psychophysics. Doesn't work for most of us. If you want to generalize to a population, and again, you assume that you did your best, you're sampling from some population, and that's good enough, you want to be able to generalize to new levels, then, and for example, an example of the first case would be like you care about specific photos of Amy and Ramesh, right? If you want to generalize to a population, maybe you say, I want the population of Ekman faces. So one particular stimulus set. Then, if you're doing an inferencing model, this is a random factor, or as I've said, in classification, you train and test out of sample on different subsets. If you want to get to the population you care about, you have to do a lot more work. I mean, that's really the bottom line, right? Again, just drawing that conclusion, that you don't stop at saying, well, this is a population. Maybe Ekman faces are not actually good representations of people's day-to-day facial expressions. So you have to sample more widely. You may have to include more complex, possibly hierarchical random effects. You may want to use post-stratification to correct after the fact if you don't think your distribution matches what is on the world, and so on and so forth. And that's hard work, right? But at minimum, I think we should almost always, at least in many designs, be aiming to generalize to a population of some sort. Okay, so let me just wrap things up. Hopefully I've convinced you that generalization is hard, right? It's actually really hard. It's really important, and we do it implicitly all the time, but it does not come for free. And we almost universally, I think, overgeneralize our conclusions in fMRI. Again, I don't want to be absolutist about this. There are people in this room who, because of the nature of the questions they're asking, don't have to worry about this at all. If you're only looking at fixed effect and you really don't work with stimuli that vary, or you have no reason to think that research site matters at all, maybe this is not, you don't have to worry about this. But for most of us, this is a serious issue, I think. And it has consequences, right? So it has consequences for false positive rates, also for overfitting in a predictive context, because that's essentially what this is. You might look like you're predicting some disorder with 92% accuracy, but of course, as soon as you change the stimuli, you're not doing so hot, right? And so, again, I'm not in a position to give you a number, and I don't think we need a number, but it is, I think, a serious concern for sure. Fortunately, there are means of addressing the problem, both via modeling, as I've showed you, but also design. And design is arguably the simplest one. If you're in a position where you really can sample many stimuli, then you should. I mean, I think there's very little reason not to go out and get 100, 200 images if you were otherwise just going to use 10 or 12. I would also add, though, and either as a compliment or maybe this should be our primary focus, that we should probably all make an effort to generalize more slowly, right? So rather than sort of making very strong claims and then sort of backing away from them as the evidence comes in, then maybe the effect does not hold everywhere, maybe we should try the opposite route, right? So we say, look, here's an effect that's constrained, and let's see if other people can demonstrate the same thing. And so I recently tweeted this, and somehow it got taken by many people as a joke, even though I was actually completely serious about this. I mean, I think this would do a lot to kind of remind us that actually most papers are highly contextualized, right? And the default assumption, I think, should be that there's not a generalizable effect until demonstrated and not the converse. But let me just close by inverting that. So here's a joke that I think is intended as a joke, but I think actually carries a very deep insight that we should all take quite seriously. This is I think, an attributed joke that's been circulating on the internet for a long time. I saw it on John Miles' White blog, and I think it really captures this nicely. So a mathematician, a physicist, and an astronomer were traveling north by train. They had just crossed the border into Scotland, and the astronomer looked out of the window and saw a single black sheep in the middle of a field. Scottish sheep are black, he remarked. No, my friend, said the physicist, some Scottish sheep are black. At which point the mathematician looked up from his paper and said, in Scotland there exists at least one field in which there exists at least one sheep, at least one side of which is black, right? And so my contention is that in brain imaging and really many other fields of science, we've been behaving for a long time like the astronomer in this story, but we should probably try to behave a little more like the mathematician. Thank you. I don't know do we take questions? Yes, no? I think I have like 2 minutes, so. Okay.
Hi, this is just amazing. As a psychologist, I'd love to point out that I see a parallel with questionnaire construction. Mm-hmm. That in questionnaire construction, at least in contemporary sense, people spend a lot of time validating the questionnaires. In a way, each question in the questionnaire is sort of a picture, an fMRI experiment. Mm-hmm. And they really spend time to show that they're burst varying, and also they hang together. And if they hang together, you can generalize. Mm-hmm. And if they don't hang together, then you could study individual items, which are, of course, interesting. So I think similar principles could be applied in stimulus validation. Either people should show really carefully that these stimuli really hang together, or they could just publish individual effects for each stimuli, and these could also be interesting. Yeah. Like if you can detect schizophrenia from one single picture, then it's amazing.
Yeah, no, I agree with that. I think that's absolutely right, that you could think of questions on a survey measure as reflecting the same principles, and you might want to actually model then the individual item as random, but depending on how the question is constructed. I don't know who's first.
So, well, very nice, really very interesting. So when we think on the random effects, we think about the population in general, about them being infinite, right? They're very large and you just get a tiny bit. So what if the population is actually also very small, countable, and you randomly use a subset of that? So it's not really fixed, but not entirely random. How do you approach that?
So that's controversial. I think there's a discussion in the literature, and some people say, well, it doesn't matter. You can still model it as random. Other people would say no. Honestly, I don't actually have a problem either way. To me, that feels like a question, and this probably some people will disagree with this as well. But to me, that depends on how you think about the question you're asking. Right. So if you think that you are trying to generalize beyond just these 5 out of 15 stimuli, maybe you fit a random effects model. If not, you don't. I don't have strong feelings about that particular issue, I guess.
So in your talk, you already mentioned a few other factors which are random effects, like scanners, investigators. So I'm going to throw in another random effect factor, which is at a lower level. So in the example you showed here, you still make one assumption, which is the hemodynamic response. So the shape of that hemodynamic response in your example is fixed. So I hope everybody agrees that the hemodynamic response shape varies across different brain regions, across different conditions or tasks, and across different groups. So suppose I want to make a relaxed study assumption. I want to adopt a model-free approach. Don't make any assumption about that. Instead, I use multiple basis functions to estimate the hemodynamic response. So by doing that, I treat the hemodynamic response as a random factor. So if I adopt the framework you are discussing here, that would be another random effect factor. So it seems to me that would be make the system unidentifiable. Have you given any thought about how to deal with that issue?
A little bit. So I alluded to this. The question of how you would model factors that are unidentifiable in a given design. You could do it by introducing priors, right? So you could have priors that say, like, here's how much variance we think these things are, even though we're fixing the observed value to what we observed. And so you're just injecting more uncertainty into the model. I totally agree with you that's one. There are probably many other things that we should be modeling as random. And there is a certain point where you kind of have to ask yourself, like, when does this stop, right? But for things that at least seem like they're tractable and that we can model, I would argue we should go after those and hopefully identify, the low-hanging fruit first. But yeah, I agree. I mean, that's a concern. I don't know if I should keep going, or I'm already 3 minutes over. So, who's the police here? Do I stop? No. I'm happy to keep going until someone kicks me off. Yeah.
One more. So, Tal, that was a wonderfully disarming talk. I was wondering if you could talk a little bit about whether you think the complexity of the stimuli being used has anything to do with this effect. So if you have to show, you have to test 52 different faces, but then you showed when using something complex like a natural story, you only have to test across 7. Do you think there's a relationship there?
There may be. I'm not in a position to say. But I mean, in a sense, the question is how big the stimulus variance is, right? And so to the degree that stimulus variance is large, this is something you should be worried about. But I mean, it's just like subject, right? It's not you're not making a general statement about you need like 20, and so I hesitate to say, well, 30 stimuli is fine. Yes, it probably varies depending on the parameters of the domain, et cetera, but until such time as we have enough studies that we can sort of, kind of like we think of like cognitive psychology as, you need fewer subjects than social, I'm not in a position to make any statement, but it probably, long-term, sure, like there will emerge some norms that say, in this domain with 40 stimuli are fine, over here you probably should have 500 of them. I think I should probably cut this off just because I'm already 4 minutes over, but I'm happy to chat afterwards. So.